Hello everyone, in this video I would like to share about how you can make your very own simple stopwatch.
It's quite easy to just copy the schematic and the code. It's quite easy to make, but the hardest part is in understanding the code. How the stopwatch works is quite simple. It has 4 digits and therefore it can show time accurately from 0 seconds to 999.9 seconds. And also the stopwatch has 2 buttons. One to stop the timer, which is the pause button, and one to reset the timer back to 0. For the table of contents, I will only explain 4 parts. The first one is about how electronics in general work, and then about the materials used for this schematic, and then the schematic itself, and finally the code. So now I would like to explain about how electronics in general work. So in every single one of power sources like chargers and laptop USB, or maybe with the one that we're using right now, which is a 9-volt battery, there will always redox reaction happening, where one part of the battery receives electrons, this is called reduction, and the other part loses electrons, this is called oxidation. And this cycle of reduction and oxidation will happen infinitely as long as the circuit is closed. And a circuit is closed when it is connected from its beginning to an end. So when you plug out the jumper wire and it's no longer connected, the redox reaction stops. And in a 9-volt battery like the one you're using, the negative terminal loses electrons and the positive terminal gains electrons. So the chemical reaction differs depending on battery type. So like the chemical reaction for a 9-volt battery is different compared to if the circuit is powered on by the laptop through a USB cable. So for a 9-volt battery, this part is not really relevant with the rest of the schematic. In summary, the negative terminal, which is the zinc, will lose 2 electrons, while the positive terminal, which is the manganese dioxide, it will gain 2 electrons. So what is voltage? Voltage is basically the potential difference between higher electrical potential energy and lower electrical potential energy. I think it's quite a wordy definition, so the simpler and easier to understand is that it's a difference between area with more electrons and area with lesser electrons. And the existence of voltage, which is the difference between higher and lower electrons, it will create electric field with the formula of electric field equals the derivation of volts in respect to the radius of the area. Electric field is the constant push making electrons move constantly from negatively charged area to positively charged area. In summary, charges attract and repel like magnets due to electric fields. So electrons are attracted to protons and will move towards protons. And lastly, electricity is another word for electric current, which is the flow of electron different by electric field. Electricity, again flow of current, flows through each component and activate the task of those components. So if there's an LED, it will make the LED get turned on. The current then returns to the positive terminal to complete the repeating loop, and it will cycle infinitely until the circuit is opened. So for the components, we first need Arduino Uno. Its code name is A000066. And alongside Arduino Uno, we will need Arduino IDE, which is like a software where we can run codes to activate the Arduino Uno. And then we will also need a 4-digit 7-segment. Its code name is 5461AS. A shift register, which is 74AC595. It is often called 595. And 4 resistors of 220 ohms. And then we also need 2 tactile push buttons, a breadboard, jumper wires, a 9-volt battery and barrel jack adapter, so we don't always have to connect the Arduino Uno with the laptop, and a USB-B to USB-C male-to-male cable. This is used primarily for the first time to connect the code into the Arduino Uno. So first, Arduino Uno is used to run codes that control electronic components in a circuit. The code is from the software called Arduino IDE, and it uses C++ with a simplified function from Arduino libraries. So it's just C++, but there are some functions and some terms that may only be common in Arduino IDE, for example, like bit set and digital write. I'll explain about those later. And then we upload the code to Arduino Uno via the USB-B, USB-C port. And in this project, the relevant Arduino parts are only the GPIO pins, which is from 0 to 13. It will be used to connect the components for the code. And then the USB-B port, we connect it with the laptop to upload the code. And then the barrel jack, it will be used to connect the Arduino Uno with a 9-volt battery. And then the 5V, which is to connect the circuit with the positive terminal, and the GND or ground, it is to connect the circuit with the negative terminal. And then there is breadboard. It is used to build electronic circuits without soldering. And as you can see in the image, the positive and negative terminal pins are connected as rows, and the normal pins are connected as columns. So for resistor, it reduces the flow of current, which is basically electricity, in a circuit. In this project, it protects Arduino Uno from receiving too much electricity. And the resistance value is measured in ohms and uses 4 or 5 colored bands. The rule is that if there are 4 stripes, the first color is the first digit, the second color is the second digit, the third color is the multiplier, which is by powers of 10, or like by 10 to the power of 2, by 10 to the power of 3, and so on. The fourth color is error tolerance. Usually it's between 1 to 5% of error tolerance. If there are 5 stripes, the third color will be the third digit, and the fourth color will be the multiplier instead, and the fifth will be the error tolerance. This project uses 220 ohms. So if the resistor has 4 bands, the color will be red, brown, and gold. Well, if the resistor has 5 bands, the color will be red, black, and gold. The last color, which is gold, it can be different, can be silver, etc., because the error tolerance usually don't matter that much to the rest of the circuit. And lastly, there is 9-volt battery and barrel jack adapter. They are used as external battery. Without external battery, the circuit must be powered through the USB-B to USB-C and laptop, which is not portable and is a bit impractical. It's very simple to use. Just connect the smaller pin on the adapter with the bigger pin on the battery, and also the bigger pin on the adapter with the smaller pin on the battery. So the next component that is needed is the shift register. It has two uses. The first one is to shift data bit by bit. Basically, to show a number, for example, like 2, it has to shift each segment of that number 2. And after all the segments are shifted one by one, the whole result will be shown as a number. Next one, it will also be helpful as it can control 8 extra GPIO pins using only 3 Arduino pins. And the 3 Arduino pins are the control pin, data pin, and latch pin. As you can see in the image, the shift register has 16 pins. To find out which pin is which, we can look at that half circle at the top. It represents the one closest to the pin number 1 and pin number 16. So there are actually 8 extra pins that we can use. Pin number 1 to pin number 7, and then pin number 15. So for pin number 1 to number 7 and pin number 15, they are used as extra GPIO pins. They can be used to replace the function of the GPIO pins. And then for pin number 8, it is the GND or ground, which is connected to the negative terminal of the breadboard. For pin number 9, it is used to connect with another shift register. However, if there is only one shift register, it shouldn't be connected with anything. As later I show in the schematic, pin number 9 for this stopwatch is not connected to anything. For pin number 10, we won't be using this pin even for the reset button later. However, we must keep it high all the time so that the circuit will work normally. So For pin number 11, pin number 12, and pin number 14, those are the three most important pins of the shift register, which are the clock pin, latch pin, and data pin. Those three pins are called control pins. They work in a sequence like this. First, latch pin needs to be set to low as an indicator that the clock pin and the data pin will work together. After the clock pin and data pin is done working, latch pin will be set to high again. And then data pin will hold the bit to be shown. For example, if the person wants to show number 1, data pin will hold 0, then 1, then 1, then 0, 0, 0, 0, 0. And when it holds 0, it will be low. And when it's hold high, it will be 1. And in between changing from low to high or staying low or staying high, clock pin will be set to high so that the bit from data pin is shifted into the shift register internal memory. So again, if you want to show number 1, data pin will hold 0. And then the clock pin changes from low to high, and the data of 0 from the data pin will be shifted into the shift register internal memory. And then the clock pin will be set back to low, and then the data pin will be set to high to represent number 1. And then the clock pin will be set to high again, and then the number 1 will be shifted into the shift register internal memory, and then clock pin will be set to low again. And then the data pin will be staying high, since after 1 it is 1 again. And then the clock pin will be set to high, that 1 will be shifted again into the internal memory, and then the clock pin will be set to low again. Afterwards, the data pin will be set to low, and the clock pin will be set to high again, and that low will be sent into the shift register internal memory, and then clock pin will be set to low again, and again until the whole byte is done. And then after 8 shiftings, the shift register internal memory will have a full byte stored. Yes, a shift register can only store 1 byte. And the output pins haven't changed yet. So once the latch pin is set to high, it will show all the 8 bits at once. And it will only show them to the LEDs and displays that are connected to pin 1 to 7 and then pin 15 of the shift register. So if the LED or the display is not connected with the shift register, it won't be shown there. And then for pin 16, it is the VCC. It will be connected with the positive terminal, which is indirectly connected with the Arduino 5V as the power source. So the last component will be the 4-digit 7 segment. It has 12 pins underneath the LED, and it has 6 pins on the upper part and 6 more pins on the lower part. And to better understand what each of these pins do, we should look at the illustration that I've made on the right. There is like 4 digits with each their own symbols of A, B, C, D, E, F, G, and a DP, which means decimal point. And then there's D4, D3, D2, and D1. D1 is the leftmost one. It is the lowest in terms of the time value. So like it's the decimal of seconds. And D2 is for seconds, D3 is for 10 until 90, and D4 is for hundreds. As you can see, all of the segments are on the same positions. So A for all of the digits are the same. B the same too. C the same too. And for the pins from bottom left to right and then upper right to left, the first pin is E. The second pin is for D. The third pin is for DP or decimal point. The fourth pin is for C. The fifth pin is for G. The sixth pin is for decimal point. The sixth pin is for digit 1. The 7th pin is for B, the 8th pin is for digit 2, the 9th pin is for digit 3, the 10th pin is for F, the 11th pin is for A, and the 12th pin is for digit 4. And yeah, these pins may differ depending on the type of 4-digit 7 segment being used. Mine is that way, and it is actually different from the ones I found on the internet. I actually had to experiment with each of the segments, what each of the pin actually show up as. And the 4 digits are represented as D1, D2, and D3, and D4. D1 is for the rightmost, as I've said before, and D4 is for the leftmost. Each of these letters from A to G represent a different LED of each digit. And this combination of letters will show certain numbers. Getting the combination wrong may mislead the number or may make it not look like any number. It looks like some weird symbol. And as you can see in the example, 1 means that the segment B and C gets turned on. 2 means EBGED gets turned on. 3 means ABC digit gets turned on. 4 means FGBC gets turned on. 5 means AFGCD gets turned on, and so on. For the code, they will be represented in an array later under a variable, and it has 8 bits. So for BC to get turned on, it must be 0, 1, 1, 0, 0, 0, 0, 0. So the 1, 1 represents position B and C. So for number 2, it has to be 1, 1, 0, 1, 1, 0, 1, 0, and so on. The last bit will always be 0 unless for digit 2. Because on digit 2, the last bit will always be 1. Because the last digit is actually the decimal point. And the decimal point will always need to get turned on digit 2. And it must always be turned off for digit 1, 3, and 4. And now this is the schematic for the stopwatch. As you can see, there is Arduino Uno, there is 4-digit 7 segment, there is shift register, and there are 2 buttons, one for reset and one for pause. From the basic observation of the schematic, there are 4 resistors, and they are to connect each of the 4 digits of the 4-digit 7 segment into the Arduino. Later I will explain about it more. So the 5 volt is connected to the shift register pin 16 or VCC for power, and ground is connected to the negative terminal of the breadboard. And then the 4-digit 7 segment have 12 pins, 8 for the segment and 4 for each digit, as I've said before. The 4 digits are individually connected with Arduino Uno, and the 8 segments are connected with shift register. Specifically, the arrangement is as written. So for the segment E, it is connected with the shift register pin number 5. For D, it is connected with the shift register pin 4. For decimal point, it is connected with the shift register pin 15, and so on. And the arrangement of the pins can actually have a lot of different variations, and it can have a lot of changes. However, the one that I've used there is well suited for the code later that I will show, and it is made for higher clarity and easier understanding of the code. So each of the 4 digits need to have 220 ohms resistor before reaching the Arduino Uno, while the ones heading to shift register don't need them. Because the general rule of using a 4-digit 7 segment is that segment pins produce less current, because they only light a single segment, while digit pins produce more current because they light a whole digit. That's why they need to have a 220 ohm resistor. And I think another side factor is that Arduino pins are a lot more expensive compared to shift registers chip. And also there are 2 push buttons, one for reset and one for pause. The one for reset is connected to GPIO 11 and for pause is GPIO 12. Pin 1 of both buttons are connected to GND and the pin 3 are connected to pin 11 and 12. So as you can see, their left pin is connected to GND both and their right pin is connected to GPIO pin both. And the shift register has some more pins left. For pin number 8, the GND is connected with the negative terminal, leading to the Arduino GND. This is expected, of course. And then for pin number 9, it is not used at all because there is only one shift register. For pin number 10, it must be made high, because if it is low, the circuit will reset constantly. And for pin number 11, the clock pin is connected to pin 9 of Arduino Uno. For 12, latch pin is connected to pin 8. And for pin 14, data pin is connected to pin 7 of Arduino Uno. For pin 13, it is connected with GND to stay low all the time, because for the display to work normally, it must be low. If it is high, then the outputs or the display won't work. So this is the summary of how the code works. First of all, we use a function called millis, and it will count time from the moment the stopwatch is connected to the power source. It will count time until infinity, and it cannot be subtracted or stopped. That's why we must find ways around that feature through creating variables that are equal to millis subtracted by some other variables. And every second in millis will be transformed into a binary pattern that represents the number of 0 to 9. And that binary pattern will be shown in the 4-digit 7 segment. For example, the number 1 in millis will become 011000000. And then for digit 7 segment will only show numbers from the first decimal until the hundreds. So after 999.9, it will automatically reset. 4-digit symbol segment, we will first pick a digit from 1 to 4, and then pick the binary pattern. And then that binary pattern will be shown in that one digit only. For example, it starts with the digit 1, which is the rightmost decimal, and it will only show that number in digit 1. It will not show number in digit 2, 3, or 4. And then it will only show number in digit 2, digit 1, 3, and 4 will not have any number shown. And then it will be shown in digit 3 only, and then digit 4 only. And then it will cycle very fast. The interval between digits shown is just 1 millisecond or 0.001 second. It changes so fast that we cannot see the delay, and this is called multiplexing. To show the 4 digits, the code uses a formula called digit extraction for display. In summary, this formula will show only one number inside that digit. For example, 43.5 seconds, it will detect 0 as the fourth digit and 0 only, and then 4 as the third digit and 4 only, and then 3 as the second digit, and finally 5 as the first digit. The rightmost bit of a byte represents a decimal point. It is hard-coded, and a decimal point will always appear on the second digit. There is also two buttons, one for pause and one for reset. When pause button is pressed, millis cannot be paused. And then shift register will shift each bit of the binary pattern one by one as told in the shift register part before. And each shifting takes about 100 microseconds. So basically it takes about 0.8 millisecond for one byte or 0.0008 second. Lastly, all the 7-digit pins of the 4-digit symbol segment are connected with shift register GPIO pins, and the 4-digit are connected with the Arduino GPIO pins, as I've said before in the schematic. Therefore, when we want to continue the stopwatch, millis must be subtracted by the duration of pausing to continue where it paused. And also, when the reset button is pressed, millis will be subtracted by itself. So it will make the stopwatch start counting from 0 again. There is also an infinite loop that will constantly check if the pause and reset button has been pressed or not to prevent double clicking. So if you want to look at the full code, it is in the link at the top of this slide. I will not explain the code sequentially, and rather I will explain it in a way that I think can be easier to be understood. So first we have to create a variable, and this variable will store all the bytes for each and every single number. For this, I call the variable segment warehouse. And as you can see, it has an array symbol. So basically, if you put a number, for example 0, 0 means it will show the first byte of this variable. And coincidentally, the first byte of this variable is also the byte symbol for number 0, which is 0B11111100. For example, if you put the number 6 inside the bracket, it will show the 7th byte of this variable. And also coincidentally, the 7th byte of this variable is the symbol for number 6, which is 0B10111110. And yeah, byte is a data type for 8 bits. And bits are true or false. And the true is symbolized by 1 and the false is symbolized by 0. Const is a modifier to not let the variable ever get changed throughout the code. Because if we let one of these bytes get changed throughout the code, we can disrupt the numbers displayed on the 4-digit symbol segment. 0B is a number format for the numbers next to it. And 0B specifically means the number next to it are binary numbers. It is also a number format for hexadecimals, for decimals, and more. There is a warning that the order of binary may change slightly based on the 4-digit symbol segment. If it is different, test each bit one by one within the brackets. And then we will have to create a new function. This function is called show one digit at a time. Basically, as I've mentioned before, that each digit is shown for only 1 millisecond, and this happens so fast that it looks as if all digits are showing at the same time constantly. This is called multiplexing again. So for show one digit at a time, we must take two parameters. The first parameter is for digit position. Is it for D1, D2, D3, or D4? And the second parameter is called segment index. Basically, segment index is the index for segment warehouse. Index is like the number inside an array. So in this scenario, as I've said before, if the index is 2, it will show the byte for number 2. If the index is 6, it will show the index for the 7th byte, which is also number 6. And later on, we will have to use another function. And in that function, digit position will instead be represented by I. And I is a repeating loop of 4 types. So if I equals 0, then it is for D1. If I equals 1, it is for D2. If I equals 2, then it is for D3. And if I equals 3, that means it's for D4. And then beneath, we can see if digit position equals 2, bit set index segment 0. So in C++, when you use bit set brackets variable, 0, it will turn the rightmost bit of that variable into 0. So in this case, the rightmost bit of index segment will become 0. This is relevant because in digit position 2, there must be a decimal symbol to represent the separation between seconds and decimals. For example, for number 1, it will set 0B010010000 into 0B010010001. The rightmost bit got changed from 0 to 1. And then shift out is also a function for shift registers. It is basically a simplification of how the data pin and the clock pin will work. To use shift out, just type shift out brackets the variable for data pin and then the variable for the clock pin, and then MSD first, and then comma the data, which in this stopwatch is the index segment. MSB first can be changed to LSB first. MSB first means that the data is shifted from left to right, while LSB first means it is shifted from right to left. And then digital write will use the variable digit position to determine which digit to choose from, and then turn on that one digit at a time from left to right by setting its pin to low, which means the digit position pin is on for 1 millisecond. After that, it will get turned off again, which means it will be made high, and then it gets turned on again, which means it will be made low again. This happens 1 millisecond for each digit, and all 4 digits look like they're on at the same time. And lastly, show 1 digit at a time is an infinite loop. It will be mentioned again later. Next, we need to create a new function called power, and this power will later be used for the math, for the digit extraction formula. Basically, long is a data type for large non-decimal whole numbers. Basically, it can be from negative 2 to the power of 31 to 2 to the power of 31. That is a very large number. And then for base number and exponent, base number will always be 10th in this code, and exponent will always either be 6 minus I or 5 minus I. And then again, I will be the representation for digit position. If exponent is 0 or less, then return 1, because any number with power of 0, the result is 1 or fractions. And if exponent is greater than 0, then the result will be based on the formula of base number, which is always 10, times hour, which in it has base number, comma, exponent minus 1. Basically, this is a repeating loop, and it is called a recursion, and it will repeat the function power again and again until the last exponent becomes 0, because once the exponent becomes 0, it will be just multiplied by 1. So yeah, this is basically just a repeating recursion. So now this part of the code shows the first half of math for segment index. And basically, math for segment index is used for the digit extraction formula. In this function definition, segment index is still called segment index, while digit position is referred to as I. It will be shown in the last part of this code. So digit position, or I, if I is equal to 0, that means it is about D1 or the rightmost decimal. If I is equal to 1, then it is about the D2 or the decimal next to the rightmost decimal, and so on. With C++, if followed by variable in the bracket means if variable is true. Therefore, the fourth line means that if post date is true. which means if the stopwatch is pausing. Posted is a variable that will be defined later. So digit extension for display formula, in simpler words, is just segment index equal the remainder of the actual time value that wants to be shown from being divided by 10 to the power of 6 minus I, and again divided by 10 to the power of 5 minus I. And the actual time that wants to be shown when being paused, which is in this page, is time right before pausing, because it will not change until the stopwatch is resumed. However, the actual time that wants to be shown when it is not being paused is merely subtracted by the total duration of pausing, and it will constantly change every millisecond. So digit position starts with 6 for a 7 second for digit because IDE uses milliseconds. If digit position starts with 4 instead of 6, then display will show 1.234 seconds instead of 001.2 seconds. Basically, the stopwatch will not work as intended. So here is an example. If time right before pausing is 8675 milliseconds or 8.675 seconds. So segment index will be equal to the remainder of 8675 divided by 10 to the power of 6 minus I divided again by 10 to the power of 5 minus I. In the first iteration, it will be the remainder of 8675 divided by 10 to the power of 6 divided by 10 to the power of 5. For this, we can use the modulo rule. If A is less than B, then the remainder of A being divided by B will equal to A. So since 10 to the power of 6 is greater than 8675, then it will stay 8675, which when divided by 10 to the power of 5 will be a decimal of 0, something. But since the data type is a long, it will stay as 0. In the second iteration, the modulo rule is used again, because 10 to the power of 5 is still greater than 8675. Therefore, it will just be 8675 divided by 10 to the power of 4, which also results in 0, something, and again the type is long. For the third iteration, the remainder of 8675 being divided by 10 to the power of 4 divided by 10 to the power of 3 will result in 8. And for the fourth iteration, the result will be 6. The final result will depict all 4 of these digits together, and therefore it will show 008.6. And then this part of the code is for if the code is running normally and is not being in a pausing state. So else means that if the stopwatch is running normally and not being paused, the formula is the same as before, but the actual time being shown is no longer just time right before pausing, but is instead merely subtracted by total pausing duration. Because the stopwatch changes every millisecond and it cannot show the time while the stopwatch is being paused. Therefore, it must be subtracted by the pausing duration. So here is an example. The total time running is 10,000 milliseconds or 10 seconds, and it is paused for 1,325 milliseconds. So segment index is equal to the total time running subtracted by the pausing duration. So 10,000 subtracted by 1,325, and the remainder of it is being divided. So segment index is equal to the remainder of 10,000 subtracted by 1,325 and later divided by 10 to the power of 6 minus I, and afterwards divided by 10 to the power of 5 minus I. And the result is basically the same as the previous page. The remainder of 8,675 from being divided by 10 to the power of 6 minus I, and then divided again by 10 to the power of 5 minus I. This is just like the previous page. The display result is 008.6. So as you can see, there is one line of code at the very bottom, which is show one digit at a time, brackets I, segment index. So basically, this just implies that the parameter is I, segment index, and I will take the position of digit position, while segment index will take the position of segment index too, so their names don't change. But for I, it changes into digit position. this part of the code, create a functions that reacts to when the pause and reset button are pressed. So in C++ and Arduino IDE, within a void loop, if there is function and inside its bracket is variable a, and then the same function and inside is variable b, and another function with inside is variable c, and then when defining said function, there is function with array of variable d, or another word for array is square brackets. That means variable d is the placeholder for variable a, variable b, and variable c. So to choose a specific variable of a or b or c from that placeholder of variable d, use switch brackets placeholder variable. So in this case, variable d. And inside its curly braces, use case variable a to choose variable a, use case variable b to refer to variable b, and use case variable c to refer to variable c. So the variable one of either button is the placeholder for variable of pause button and reset button. So in defining the check button press function, we use switch brackets one of either buttons, and then inside its curly braces, we use case pause button for what happens with the pause button, and then case reset button for what happens with the reset button. We will be explained later. So button ready to press is a variable that will be defined at the top. However, I'm not explaining this code. As I've said again, I'm not explaining this code narratively. And it is true by default. So in this function definition, button ready to press will become false after the placeholder becomes low. So after the button is getting pressed. So if the placeholder of which is one or both of the buttons becomes low, and one or both buttons are ready to be pressed, then there will be two outcomes, case 1 and case 2. Case 1 is if the button is pause button, and case 2 is if button is the reset button. So as we remember before, in the function of math for segment index, there are two formulas. First, if the stopwatch is in a pausing state, which is the button is already pressed, or if it is not, in which the actual time being shown is either time right before pausing or millis subtracted by total pausing duration. In this case, time right before pausing will receive their new value every time the stopwatch is getting paused, and total pausing duration will receive their new value every time the stopwatch is getting resumed. To get total pausing duration, total time needs to be subtracted by time right before pausing, and to get time right before pausing, total time needs to be subtracted by total duration of pausing. So here is an example. The starting stopwatch is at 0. So we run it for 100 seconds and then we pause. Therefore, the time right before pausing is equal to millis subtracted by total pausing duration, which is 100 subtracted by 0. 0 because it has not even been paused yet, it just started. Therefore, the actual time shown will be 100. And then we wait for 20 seconds and then we resume. Therefore, the total pausing duration will be equal to millis subtracted by time right before pausing, which is 120 subtracted by 100, and it is equal to 20 seconds. And since this is in an unpausing state, the actual time shown will be 120 subtracted by 20, which is equal to 100. So we run it again for 150 seconds and then we pause. Therefore, the time right before pausing will be equal to millis subtracted by total pausing duration, which in the statement before, it has been paused for 20 seconds. Therefore, the total pausing duration will be 20. So 170 subtracted by 20, the actual time shown will be 150. And then we wait again for 30 seconds and then resume. The total pausing duration will be equal to millis subtracted by time right before pausing. And since we waited for 30 seconds, the millis will be 200 subtracted by 150. The result is 50 seconds. Therefore, the actual time shown will be 200 subtracted by 50, which is equal to 150. In this page, it is for the second case in which the reset button is being pressed instead of the pause button. The result will just be the activation of the reset function, which will be defined and explained later. And then we make the button not ready to get pressed. So after pressing either the pause button or the reset button, we will make that button not ready to get pressed. And it will be made ready to press again once the hand has been released from the button. Therefore, the button will be returned back to high and the button will be ready to press. If we still hold on the button, it will still stay low and it will not be ready to press. So, in a scenario where the stopwatch is being unpaused, the total pausing duration will be equal to millis. This will restart the stopwatch because the formula for the index is segment index equal actual time value, and the actual time value is millis subtracted by total pausing duration. So if total pausing duration is millis, therefore millis will be subtracted by millis again, and it will be equal to 0. However, if the stopwatch is being paused and the reset button is being pressed, it will change the variable time right before pausing into 0. The formula for when it is paused equal time actual value, and it will be have remainder divided by power 10 blah, blah, but the actual time value is just time right before pausing. And therefore, if it is forcibly made 0, the depicted time will just be 0. It will just be reset. So here is how reset will affect the check button press function. So this is basically the same as the example before, except I add the last 5 lines. The first one is after 20 seconds, the reset button is being pressed. The reset function is being activated. Therefore, the total pausing duration will be equal to millis, which is 200. Therefore, the actual time zone will be 200 subtracted by 200. Therefore, the result is 0. And then after 50 seconds, we pause. And this is from the previous page. The total pausing duration will be equal to 200 because over time the pausing duration of the previous task still compound up to now. And therefore, millis subtracted by that pausing duration will be 250 subtracted by 200 equal 50. And the actual time shown will be 50. And then for the next step, we wait until 40 seconds and then we resume. The total pausing duration will be equal to millis subtracted by time right before pausing. And the time right before pausing is 50. Therefore, 290 subtracted by 50 will be equal to 240. And the actual time shown, since it is unpaused, will be millis subtracted by total duration of pausing, which is 240. Therefore, the result will be 50 seconds. And after until 60 seconds, we pause again, which will be millis subtracted by total pausing duration. And the actual time shown will just be time right before pausing, and that will be 250 subtracted by 240, and the result is 110. And lastly, we wait for 30 seconds and then we reset. Therefore, the time right before pausing will just be forcibly made 0 because the last line of this void reset function is just time right before pausing equals 0. 0, the remainder of 0 being divided by 10 to the power of 6 minus I divided by 10 to the power of 5 minus I will just be 0 because the actual time that was to be shown is just 0. So this slide shows how the pins of the shift register, the 7-segment display, and the buttons are connected to Arduino Uno. So the clock pin is connected to Arduino GPIO pin of number 9, the latch pin for GPIO pin 8, and data pin for GPIO pin 7. And then all these digit position pins, the one from the rightmost to the leftmost, in order they are at GPIO pin 2, GPIO pin 3, 4, and 5. And then for pause button and reset button, the pause button is referred to as 0 and reset button is referred to as 1. This will be relevant later as part of the array for button ready to press or not. And then the variable tactile push button with array equal 12,11. If it is 0, then it is referring to the pause button, which is the 12. So pause button is the one on the 12th GPIO pin on the Arduino, and the reset button is the one on the 11th GPIO pin on the Arduino. The next slide shows the global variables, and there are 4 of them. The first one is time right before pausing, and the second one is total pausing duration. They are both 0 because their value is equal to millis subtracted by the other one. So time rate for pausing is millis subtracted by pausing duration, and pausing duration is equal to millis subtracted by time right before pausing, and it will be defined in the function about the checking button states. And then for button ready to press or not, if it is filled with 0, then it is referring to the pause button. And if it is filled with 1, then it is referring to the reset button. And both of them are true. Also, when starting the code, the pausing state will equal to false. They will become true later once the pause button has been pressed in the function that monitors whether the pause and the reset button has been pressed or not. And also there is a loop for the check button press for both the pause button and the reset button that is happening constantly. And there is also method for segment index happening infinitely inside the loop. And lastly, for setup. Setup is a function to set certain pins as input, which is receive data, output to create data, or input pull-up, which is basically just as input, except it receives data starting as high or true instead of false or low, which is the default one. So when high, it means that the 4-digit decimal segment is turned off, and when some digit gets turned on, it will be made low. So all the 3 control pins, which are the clock pin, latch pin, and data pin, are outputs because the data pin sends high or low bits to internal memory. And main clock pin sends signal of high or low to the shift register for when the data pin have to shift its bit into the internal memory. And the latch pin also sends signal for when it is ready to display the result in 4-digit table segment. It is ready when both the clock pin and data pin is done shifting each other. And then D1, D2, D3, and D4 are also set as outputs. And yeah, it's just a bit excessive to use a whole loop of I equals 0 to 3. It's just worded like that, like pin mode, each of them individually getting set as output. And then both buttons are set up as input pull-ups. Again, because input pull-ups is the common setting for buttons to prevent being activated unintentionally. They have to be made high by default and then low when being pressed. So yeah, this is basically how you can make your very own simple stopwatch.
So thank you for watching this video. I will post more schematics and tutorials in the future, and the next one will be about how to make a simple piano. That's all.